Okay, I want to welcome you to the waves equation worksheet. Let's start with this problem here. It says red light has a wavelength of 8.80 times 10 to the minus 4th meters, and we want its frequency. We want to know the frequency. In order to work this problem, we need to understand a couple of things. The first thing we need to know is that red light is part of the visible spectrum, which is part of the entire electromagnetic spectrum, which means this. It means that the speed of that wave is 3.0 times 10 to the 8th, or the speed of light. Nothing travels faster than the speed of light, but all electromagnetic radiation travels that fast. Now they're telling us that we want to calculate the frequency. So we're going to need the frequency, the equation that relates speed of light to wavelength and to frequency. And here it is. It's the speed of light, or C, is equal to the wavelength, and I'll denote that by lambda, times the frequency. I'll use a capital or a cursive F to denote frequency. Speed of light in meters per second is equal to the wavelength in meters times the frequency in hertz, or 1 per second. Now I need to manipulate this formula so that I can get at what I'm looking at. Remember, I'm looking for frequency. That's this value right here. So what I'm going to do is I'm going to divide both sides by lambda. That'll eliminate lambda from this side entirely, and then I'm left with frequency by itself. That's what I want. So I say the speed of light, that's 3.0 times 10 to the 8th. Remember, the unit is meters per second. That's a velocity. Divided by the wavelength. They tell me that the wavelength is 8.80 times 10 to the negative 4 times 10 to the negative 4, and that's in meters. So I'll put meters right here. Let's talk a little bit about units. Remember, meters and meters on top, meters on bottom, are going to cancel, leaving me with 1 per second. That unit is called a hertz. So I'll put hertz right there. Now, if you're not comfortable entering numbers in with exponents into the calculator, watch the video podcast on doing that. Make sure that you're very comfortable putting this in, using the EE key to put in 3.0 times 10 to the 8th and dividing it by 8.80 times 10 to the minus 14th, or minus 4th. We won't cover that here, but make sure you watch that one if you need help. And when we do that, the value that we get is this. We get 3.4 times 10 to the 11th hertz. 3.4 times 10 to the 11th hertz. I want to tell you that some people use this chart right here. I'll enlarge it just a little bit, but it makes it, for some, easier to know what to divide. We'll put a C right there, a lambda right there, and a frequency right there. Now you have to memorize the triangle, but as long as you memorize it, once you memorize it, you're going to know, do I multiply, do I divide, what do I do to get at what I want? In this case, remember, I wanted frequency, so if I want to know frequency, I'll cover up frequency. That leaves me with speed of light divided by lambda, speed of light divided by lambda. If I wanted to know wavelength, I would cover up wavelength. That would leave me with speed of light divided by frequency. So I can use this little diagram then, if I want to help me to remember what I do to arrive at what it is that I'm looking for. All right, so 3.4 times 10 to the 11th hertz for number 1. Let's take a look at another problem. Number 2, we have this. It says an X-ray has a frequency of 6.8 times 10 to the 18th hertz, and we want to calculate the wavelength of this light in meters. So we're looking for wavelength this time. Again, though, it's the same relationship. We're going to need the relationship between the speed of light, C, wavelength, lambda, and the frequency. So I'll call that cursive F. Now, in this case, I'm looking for wavelength, right? I'm going to go ahead and use my little help device. I'll put a triangle, put a C here, and a lambda here, and a frequency here. Again, I'm looking for wavelength, and so I'm going to cover up wavelength, and it says wavelength is equal to speed of light divided by frequency. So I say wavelength is equal to speed of light divided by frequency. Remember, if you want to use it, use it. If not, if you're more comfortable just doing algebra, then do algebra. So we've got the speed of light then, remember, is 3.0 times 10 to the 8th, that's meters per second, divided by the frequency in hertz, 6.8 times 10 to the 18th. So I say 6.8 times 10 to the 18th. I'm going to, instead of hertz, write 1 per second. That'll help me with the units. Seconds on top, seconds on bottom are going to cancel, And when I finish, I'm going to be left with meters. That's wavelength. Okay? Now, when I do that, here's what I get. I get 4.4 times 10 to the negative 11th meters. Let's talk a little bit about significant digits. I've got 2 on the top, I've got 2 on the bottom. I can only take 2 significant digits in my answer. Remember, this part, the exponential part, doesn't affect significant digits. So I have 4.4 times 10 to the negative 11th meters. And that is number 2. Okay? Let's take a look at another problem. Number 3 says this. It says a television station sends a signal at a frequency of 108.4 times 10 to the 6. Now it's frequency, so that's going to be in hertz. We want to know how much energy this time. Notice this time I'm being asked for something else. I'm being asked for energy, and joules does this wave have. What I'm going to need now is the relationship between energy, a number called Planck's constant, and the frequency. And here's that relationship. We have energy in joules is equal to Planck's constant, I'll give you that number in just a moment, times the frequency. I'll use an F to denote that frequency. So energy is equal to Planck's constant times the frequency. Now, I'm looking for energy, so it's just a matter then of multiplying these two numbers. Planck's constant is this value, 6.626 times 10 to the negative 34 joule seconds. Yes, that's joule seconds, not joules per second. So make sure we get that. It's joules seconds, both in the numerators, both units in the numerator, times the frequency. In this case, the frequency they're telling me is 108.4, 108.4 times 10 to the 6th, and that's hertz. I'm going to write it as 1/seconds, and you'll see why in just a moment. When I multiply those, and again, if you're not comfortable with exponents on the calculator, make sure you watch that video podcast on entering numbers into the calculator. I get this number, 7.183 times 10 to the negative 26, times 10 to the negative 26, and that's joules. How did I get joules? Joule seconds and 1/seconds, multiply that together to give me just joules. I'm left with just joules. 4 significant digits here, 1, 2, 3, 4. 4 here, that 0 counts because it's trapped. 4 significant digits in my final answer. Again, if I wanted to, I could have used this triangle just like this. We have energy here, Planck's constant here, and frequency right there. If I want to know energy, I cover up energy. Energy is equal to Planck's constant times frequency. If I want to know frequency, it's energy divided by Planck's constant. Okay, so use that device if you need that. All right, let's go on to the next one. Number 4. And number 4 says this. It says, what is the frequency of a radio wave with an energy of 2.65 times 10 to the minus 24th joules? Another energy problem. They're giving me the energy this time, and they want to know the frequency. So what equation do I use? We have energy is equal to Planck's constant times the frequency. I'm looking for frequency. So I'll underline frequency to remind myself that that's what I'm looking for. I'll divide both sides by Planck's constant to get frequency. So h divided by h, or Planck's constant divided by Planck's constant, cancels away and leaves me with frequency. And I'm left with energy divided by Planck's constant is equal to frequency. So their energy they're telling me is this value. It's 2.65 times 10 to the negative 24th, and of course that's in joules. Planck's constant is this value. It's 6.626 times 10 to the minus 34. Remember the unit there is joule seconds. Joules and joules go away, and I'm left with 1/seconds. That, of course, is a hertz. So I'll put hertz right there. And the value that I get for that is this value, 4.00 times 10 to the 9th, times 10 to the 9th. Okay, again, if you had wanted to use this diagram right here, it would have been this. It would have been energy on top, Planck's constant here, and frequency here. I'll write it as an F, and frequency right there. And I'm looking for frequency, so I'll cover up frequency. Frequency is equal to energy divided by Planck's constant, and I'm done. 4.00 times 10 to the 9th, 3 significant digits. Okay? Let's go on to the next one. Number 5. Number 5 says this. It says, when potassium is heated, a blue spectral line whose energy is 4.36 times 10 to the minus 20 is produced. What is the frequency? What's the frequency of this lighting, of this light? So we're looking for frequency, right? Now they're telling me that the energy is 4.36 times 10 to the minus 20. So what I'll do is I'll write my formula for energy. Energy is equal to Planck's constant times frequency. You know what? Let me replace that. It's sometimes written as a cursive V, but I think it's easier just to be consistent and use the cursive F. Okay? So energy is equal to Planck's constant times frequency, and they want to know what the frequency is. If I use my little diagram, either way, if I use the diagram or not, it doesn't matter. I get this. Frequency is equal to E divided by Planck's constant. So the energy they're telling me is this value, 4.36 times 10 to the negative 20. Planck's constant is 6.626 times 10 to the minus 34. Let's get units right. Energy on top, so that's joules. Bottom is joule seconds. That's the unit for Planck's constant. And so here's what I've got. I've got joules and joules canceling. I've got 1 over seconds. What's that? Hertz. Okay, so I'll put my unit of hertz right there. And the value that I get is this. 6.58 times 10 to the 13th. 6.58 times 10 to the 13th hertz. And I'm done with number 5. Okay? All right. Hopefully you're getting the hang of this. Okay, you just got to keep practicing. Do problem after problem until you've got it down. Let's look at number 6. Number 6 says this. It says, what is the wavelength of the light described in the previous question? What is the wavelength of the light described in the previous question? So we calculated a frequency. Now we're looking for wavelength. Well, remember that the relationship between wavelength and frequency for all electromagnetic spectrum waves is this. Speed of light is equal to wavelength times frequency. So I simply look to see what I'm being asked for. In this case, it's wavelength. So I'll solve for wavelength. So C divided by frequency is equal to the wavelength. Again, I could have used my little triangle. And so I'll fill in. We get 3.0 times 10 to the 8th, that's meters per second, divided by the frequency. And the frequency that we're looking for is in the last problem, and it's this number right here. It's 6.58 times 10 to the 13th. I could write hertz, but it's easier for me to write 1 over seconds because I'll know to cancel seconds with seconds, and I'll be left with meters, which was what I'm looking for. I've got 2 significant digits here, 3's here, so I can only have the lesser of the 2, 4.6 times 10 to the negative 6 times 10 to the negative 6 meters, and I'm done. All right? Again, continue to practice. Okay? That's the key. We have 2 formulas on this worksheet, and that's speed of light is equal to wavelength times frequency, and energy, for the second one, is energy is equal to Planck's constant times frequency, and that's it. Let's take care of this last one. It's a little bit more involved. I'm going to write a little bit smaller this time. It says gamma radiation has a wavelength of approximately 2.1 times 10 to the minus 11th meters. Now we want to determine the energy of this type of radiation. Remember the formula that we've got is this. It's energy is equal to Planck's constant times frequency. That's the formula for energy. Unfortunately, they're not giving me frequency, they're giving me wavelength. So what I'm going to have to do is use this formula first. Speed of light, it is electromagnetic radiation, times the frequency, and then solve for frequency by saying speed of light divided by the wavelength, okay? I'll get frequency and then plug that number right in there, and it'll give me the number that I'm looking for. It'll give me the energy. So we've got this. We've got 3.0 times 10 to the 8th. That's meters per second, of course, divided by the wavelength. Well, the wavelength they're telling me is 2.1 times 10 to the minus 11. So we have 2.1 times 10 to the negative 11, and that's meters. Okay? Meters will cancel with meters, and I'm going to be left with hertz. I'll write hertz right there. And the value that I get for that is actually it is 1.4 times 10 to the 19th. So I get 1.4 times 10 to the 19th. Again, if you're not comfortable with entering exponents in your calculator, make sure you watch that video. 1.4 times 10 to the 19th, two significant digits here, 2 here, 2 here. I'm going to take that number and I'm going to plug it right there. So we get now energy, that's what I'm looking for, is equal to Planck's constant, 6.626 times 10 to the minus 34, that's joule seconds, times, I'm going to have to come down here just a little bit, times frequency. That value is 1.4 times 10 to the 19th. 1 over seconds is the same thing as hertz. Seconds and seconds cancel, and I'm left with joules, which is what I'm looking for. And my final answer for that problem is this: 9.3 times 10 to the negative 15th joules. A little bit more involved in this problem, okay? Practice and practice until you can get them right. Folks, I'll see you on the next video podcast. That's all for waves. I'll see you then. Thank you.